Dear B.Sc second year semester third students, myself Satish Kumar Kamble, Department of Physics, Abasai Marathe Arts and Newcomers Science College, Rajapur. So, in the last lecture, we have seen the introduction about the optical properties. We have just started. We had started the unit third, that is the properties of material of paper third of B.Sc semester third. In that we have started the optical property chapter. We have introduced the chapter. Now today we are going to study some new things about the chapter. So let us start with absorption, reflection and transmission, that is refraction. The optical properties of matter, for example, refractive index, reflectivity, absorption coefficient, etc., affect the light reflection and transmission of electromagnetic or light radiation. Also, we have seen that the optical phenomenon that occurs within solid materials involve interaction between electromagnetic radiation, that is the light energy, uh, and the atoms, ions, or electrons of the solids, which gives rise to physical process such as absorption, reflection, and transmission. Okay. Again, we have seen the electromagnetic radiation, electromagnetic spectrum also. In the last chapter, last video lectures, we have studied the electromagnetic spectrum also. Now, uh, from this figure, if I naught is the incident ray, and this one is nothing but the first reflected ray. Then from the conservation of energy, we have seen the equation I naught equal to IR plus IT plus IA, where I naught be the intensity of the incident radiation, IR be the intensity of partially reflected beam, then IT is nothing but the intensity of partially transmitted beam. Again, IA is nothing but the intensity of partially absorbed beam. Okay. Then from the conservation of energy, I naught equal to IR plus IT plus IA. Now today we are going to study the process of reflection, absorption, and transmission of electromagnetic radiations in solids. So, so we have seen that the all materials interact in some way with light, means electromagnetic radiation. In electromagnetic radiation or light is nothing but the stream of photons. So photons are electromagnetic radiation with zero mass. Again, photons have the zero charge, and the velocity of the photon is always equal to c, means 3 into 10 to the power 8 meter per second. That is the speed of light. Because they are electrically neutral, they do not steadily lose energy via Coulombic interactions with atomic electrons, as charged particles does. If the incident photons interact, with the valence electrons, then number of things can happen there. For example, the interaction of light energy or the electromagnetic radiation or the photon with the uh, valence electron, or we can say with the material, causes the number of things in which, for example, photons means electromagnetic radiation gives up their energy to the material and the absorption process occur. Again, photons may give up their energy, but photons with identical energy are immediately emitted by the material and therefore the reflection occurs. Again, we have also seen that the photons may not interact with electronic structure of the material, then the transmission occurs. But in transmission, photons are changed in their velocity, okay, and a refraction occurs. So again, we have seen about this figure that incident beam or incident radiation of intensity I naught may be partially reflected, uh, partially reflected. Here is the intensity IR of the reflected beam here, and again this incident radiation can partially transmitted. Here IT is the uh, intensity of the transmitted radiation, and it can be partially absorbed, that is with the intensity IA. Here in this figure it is not shown there. Therefore we got this expression I naught equal to IR plus IT plus IA. So again it should be here noted that a reflection may occur at both the upper surface of the material and the lower surface of the material. Upper surface can also be called as the front surface, and lower surface can also be called as the BACK back surface. So the reflection may occur at both the front and back surfaces of the material. Also, part of the light energy gets scattered and utilized for the luminescence. Several factors in this case are important in determining the behavior of the incident photon, with the energy required to excite an electron to higher energy state being of particular importance. Now, today we are going to study these factors, that is absorption, reflection, and transmission or refraction. Okay, so let us study these objects one by one. So let us talk about reflection first of all. So when a photon, that is the electromagnetic radiation is transmitted to the material, it causes the polarization of electrons in material, and by interacting with the polarized material, it loses some of its energy. If the permittivity of the medium is epsilon and the magnetic permeability of the medium is mu, then the speed of light c can be related as c equal to 1 divided by square root of nu epsilon. Okay, you have to remember this equation. It is the velocity of light in terms of the permittivity and permeability. Okay, here nu is the magnetic permeability of the medium, whereas epsilon is nothing but the permittivity of the medium. Okay, so when a photon is transmitted through the material, means when the electromagnetic radiation is propagated through the material, then the electromagnetic radiation or the photon can cause the polarization of the electrons of the material, and by interacting with the polarized material, the photon or the electromagnetic radiation loses some of its energy. Okay, and we got this equation here. So optical materials generally not magnetic. Okay, optical materials that we are seeing here, the optical materials, we have seen that the magnetic permeability of the material is existed there, but in case of the optical materials, generally they do not have the magnetic and uh, sorry, optical materials generally are not the magnetic, and therefore the permeability can then be neglected in that case. That is, in the case of the optical materials, permeability can be neglected. Again, since the speed of photons decreases, the beam of photon changes direction. Okay, here we can see here is the incident radiation, or the photon is incidenting on the material surface, and this electromagnetic radiation or the photon is uh, interacting with the material medium here. So while it is in crossing, while the photon is crossing the interface of the material, then the speed of the photon decreases here, and the beam of photon changes the direction here. Here is the direction of the incidenting photon. Then after inserting into the material medium, it changes the direction here. Okay, now when it enters into the material, uh, the first beam of the photon changes the direction here. Okay, again, suppose photons traveling in a vacuum. If photons are traveling through the vacuum and they are incidenting on the material, then the refractive index of the material, in that case we can define here in this way. Okay, so in optics, the refractive index of the material is the dimensionless number which describes how fast light travels through the material, and it is defined as the refractive index. It is symbolically represented by the letter mu or m, but in this case we have represented mu by the electrical permittivity of the medium. So instead of taking mu here, we will take here n as the refractive index. So refractive index is defined as the speed of light in vacuum divided by the speed of light in material. See here in this figure, let us consider that here is the interface of the material here, interface of the medium. Here it is considered as the vacuum, and it is the sum of the medium here. And the photon or the electromagnetic radiation is propagating through the vacuum, and it is entering into the material. Okay, as these photons enters through this material, then their speed get decreases, and again the direction of the photon will change here. Okay, so photons are traveling in a vacuum, and they are allowed to enter uh, through the material. Then in that case the refractive index can be defined by this equation, that is refractive index is equal to speed of light in vacuum, that is it is nothing but c, which is equal to 3 into 10 raised to power 8 meter per second, and divided by speed of light in the material, that is v. Okay, this is the standard definition of the refractive index. Again, for example, the refractive index of the water. What does the refractive index means? The refractive index of the material is the dimensionless number which describes how fast light can travel through the material. Okay. Again, for example, the refractive index of water, we know that the refractive index of the water is 1.333. What does it mean? It means that the light travels 1.333 times slower in water than in vacuum. Okay? In vacuum, the speed of light is equal to c. Okay? But when it is traveling through the water, then the speed of uh, that light get decreases. Okay, so the light travels 1.333 times slower in water than in a vacuum. So increasing the refractive index means here vacuum is here and material medium is here. Here the refractive index is increased and here okay. Again, increasing the refractive index corresponds to the decreasing the speed of light in the medium. Okay, so in vacuum there is a speed of light is nothing but c. Okay, but whereas in material the speed of light decreases and it is given by the small v letter. Okay, here c is always greater than v. Okay. Now further we will see about the Snell's law. Again about this uh, figure we can see here the frequency of the light does not change with light gets refracted. Okay, frequency remains same here. Now let us talk about the Snell's law. So Snell's law states that the ratio of the sines of the angle of the incidence and refraction is equivalent to the ratio of phase velocities. Okay, sine ratio of the sines of the angles of the incidence and refraction. Here theta 1 is the angle of incidence and theta 2 is the angle of refraction. Okay. So it is the ratio of the sines of the angles of incidence and refraction which is equivalent to the ratio of the phase velocities in the two media, or it is equivalent to the reciprocal of the ratio of the refractive index. Okay, means sine theta 1 divided by sine theta 2 equal to n2 divided by n1. Okay, here we have taken the reciprocal of all these things. Again, if the photons are traveling in material medium 1, here is what material medium first is here with the refractive index n1. Here is the another medium which has the refractive index of n2. Again, the condition is that n2 is greater than n1, means the refractive index of this shaded medium is greater than the refractive index of this plane medium. Okay, so if the photons are traveling in material 1 instead of uh, vacuum in vacuum and then pass into the material second, the velocities of the incident and a refracted beam depend on the ratio between their indices. Okay, means here ratio of the indices of the refraction and also cause the change in the direction of the beam. Okay, so uh, sine theta 2 divided by sine theta 1 is equal to V2 divided by V1. Again, it is equivalent to ratio of the refractive indices of the both media, that is N1 divided by N2. This equation is nothing but the Snell's law. When a ray of light enters from the material with refractive index N1 into the material of refractive index N2, and if N2 is greater than N1, then the ray is bent towards the normal and away from the boundary surface. Okay. The beam traveling through material 1 is reflected rather than transmitted if the angle of refraction becomes 90 degrees. Now, again, the complex refractive index N star can be expressed by this equation, that is N star is equal to N into 1 minus IK, where K is the parameter which is known as absorption index. Okay, and I equal to square root of -1 is nothing but the imaginary number. So the absorption index can be given by the relation K equal to alpha lambda divided by 4 divided by pi divided by n. Okay, here pi is the linear absorption coefficient, whereas lambda be the wavelength of the light and n is the refractive index. Okay, further, more interaction of the photons with the electronic structure of the we can say material occurs when the material is easily polarized. Again, the refractive index n is not constant for a particular material. The wavelength or the frequency of the photons affects the index of the refraction. Okay. Again, the dispersion of the material can be defined as the variation of the refractive index with wavelength. That is dispersion lambda equal to dn divided by d lambda.